Welcome to Gamma Classroom. Today I'm going to introduce the video 1.1-3 Current and Voltage. In previous video, we learned the conductor, insulator, current flow, and electrical circuits. The main points in previous video. In conductive materials, the out electrons in each atom are called free electrons. In insulating materials, the out electrons are not so free to move. All metals are electrically conductive. Dynamic electricity or electrical current is the uniform motion of electrons through a conductor. A circuit is an unbroken loop of conductive material that allows electrons to flow through continuously without beginning or end. The location of a brick in a circuit is irrelevant to its inability to sustain continuous electron flow. Any brick anywhere in a circuit prevents electron flow throughout the circuit. As was previously mentioned, we need more than just a continuous path circuit before a continuous flow of electrons will occur. We also need some means to push those electrons around the circuit. Just like marbles in a tube or water in a pipe, it takes some kind of influencing force to initiate flow. With electrons, this force is the same force at work in static electricity. The force produced by an imbalance of electrical charge. If we take the examples of wax and wool, which have been rubbed together, this we already learned in video 1.1-1. We found that the surplus of electrons in the wax is negative charge, and the deficit of electrons in the wool is positive charge, creates an imbalance of charge between them. This imbalance manifests itself as an attractive force between the two objects. If a conductive wire is placed between the charged wax and the wool, electrons will flow through it, as some of the excess electrons in the wax rush through the wire to get back to the wool, filling the deficiency of electrons there, like this. The imbalance of electrons between the atoms in the wax and the atoms in the wool creates a force between the two materials. With no path for electrons to flow from the wax to the wool, all this force can do is attract the two objects together, like this. Because they have no path in between the two materials, they only can do is attract each other. Now, adding a conductor bridges the insulating gap like this. Put the wire between the two materials. The force will provoke electrons to flow in a uniform direction through the wire, like this. If only momentarily, until the charge in that area neutralizes and the force between the wax and the wall diminishes, like this. You see all the electrons from the left going to the right. So all the atoms neutralized because the electrons go back to the atoms. So there is no attraction between the two materials right now. The electrical charge formed between those two materials by rubbing them together serves to store a certain amount of energy. This energy is not unlike the energy stored in a high reservoir of water that has been pumped from a low-level pump, like this. This is a pump. They have the water pumper. The pump pumps the water from the low level to the high level. And the high level is stored the energy. The influence of gravity on the water in the reservoir creates a force that attempts to move the water down to the lower level again. If a suitable pipe is run from the reservoir back to the pump, water will flow under the influence of gravity down from the reservoir through the pipe like this. This is energy released. This is the reservoir. The water is in the high level. Through this pipe and go back to the pump. It takes energy to pump that water from the low level pump to the high level reservoir, and the movement of water through the piping back down to its original level constitutes a releasing of energy stored from previous pumping. If the water is pumped to an even higher level, it will take even more energy to do so. Thus, more energy will be stored, and more energy released if the water is allowed to flow through the pipe back down again, like this. This is a pump. This is a pump. It pumps the water to the reservoir and store the energy, and from through the pipe, they release the water back to the pump. Electrons are not much different. It means it's the same, almost the same principle. If we rub wax and wool together, we pump electrons away from their normal levels, creating a condition where a force exists between the wax and the wool. As the electrons seek to re-establish their former positions and balance within their respective atoms. Like this. This is a positive. This is electric charges. It means like this, a pump It's reservoirs. This is the gravity. The water through the pipe because of the gravity. So back to the pump. Same with the electrical charge. This is a negative charge, means it's more electrons. This is a positive charge, means it's less electrons. They have the attraction force, like the gravity. So they will attract the electrons, go back to the positive. If you put the path between the two charges, the electrons will flow to this and get neutralized here. Just as the pumping of water to a high level results in energy being stored, pumping electrons to create an electric charge imbalance results in a certain amount of energy being stored in that imbalance. And just as providing a way for water to flow back down from the higher heights of the reservoir results in a release of that stored energy, providing a way for electrons to flow back to their original levels results in a release of stored energy. When the electrons are poised in the static condition, just like water sitting still high in a reservoir, the energy stored there is called potential energy, because it has the potential of release that has not been fully realized yet. When you scarf your rubber soled shoes against a fabric carpet on a dry day, you create an imbalance of electric charge between yourself and the carpet. The action of scarfing your feet stores energy in the form of an imbalance of electrons forced from their original locations. This charge, called static electricity, is stationary, and you won't realize that energy is being stored at all. However, once you place your hand against a metal door rubber with lots of electron mobility to neutralize your electric charge, like here, like the picture shows, when your hand will touch the door rubbers, that stored energy will be released in the form of a sudden flow of electrons through your hand, and you will perceive it as an electrical shock, because you have the lot of the electrons in your body come from the carpet. When your hands will touch the door rubber, the electrons will go through your hands, go back to the positive, because this is metal. This potential energy, stored in the form of an electric charge imbalance and incapable of provoking electrons to flow through a conductor, can be expressed as a term called voltage, which technically is the measurement of potential energy per unit charge of electrons, or something a physicist would call specific potential energy. Everybody knows the battery. We use a battery a lot in our life. This is a battery. You always see like the positive and negative. It means it's a voltage equals 1.5 V water. It means it's 1.5 voltage. Define it in the context of static electricity. Voltage is the measure of work required to move a unit charge from one location to another against the force which tries to keep electrical charges balanced. In the context of electrical power sources, voltage is the amount of potential energy available, work to be done, per unit charge, to move electrons through a conductor. Let's take a look at this picture. They have 2 points. This is the high potential. This is the low potential. The voltage means that how much work do we need to move 1 unit of the current, like this one, from this point move to this point. We call the voltage. Because voltage is an expression of potential energy, representing the possibility or potential for energy release as the electrons move from one level to another. It is always referenced between 2 points. Consider the water reservoir analogy. This is a reservoir. This is the one location. Location 1. This is location 2. So this water drop, the energy is smaller. And this, the distance or height is bigger. So this drop is bigger. So voltage is the same. It's right from 2 points. 1 point this one, 1 point this one. Or 1 point this one, or 1 point this. Because of the difference in the height of the drop, there's potential for much more energy to be released from the reservoir through the piping to location 2 than to location 1. The principle can be intuitively understood in dropping a rock, which results in a more violent impact. A rock dropped from a height of 1 foot, or the same rock dropped from a height of 1 mile. Like this is 1 foot high, this is 1 mile high. Obviously, the drop of the greater height results in greater energy released, a more violent impact. We cannot assess the amount of stored energy in a water reservoir simply by measuring the volume of water any more than we can predict the severity of a falling rock's impact simply from knowing the weight of the rock. In both cases, we must also consider how far those masses will drop from their initial height. The amount of energy released by allowing a mass to drop is relative to the distance between its starting and ending points. Likewise, the potential energy available for moving electrons from one point to another is relative to those 2 points. Therefore, voltage is always expressed as a quantity between 2 points. The analogy of a mass potentially dropping from one height to another is such an apart model that voltage between 2 points is sometimes called a voltage drop. There are 2 pictures showing here. This one, the distance between the 2 points is short. This picture showing this 2 point is longer. That means the energy that is required to move the charge, the unit charge from this point to this point is less than the energy that moves this charge from this point to this point. It means this picture showing the voltage is higher and this voltage is lower because the distance is short. Voltage can be generated by means other than rubbing certain types of materials against each other. Chemical reactions, radiant energy, and the influence of magnetism on conductors are a few ways in which voltage may be produced. Respectively, examples of those 3 sources of voltage are batteries, solar cells, and generators, such as the alternator unit and the hood of your automobile. This is a chemical reactions. They have the zinc metal. This is a copper metal. This is zinc sulfate. This is a copper sulfate. If connect the wire in the bubble, the bubble will be gone. This is like the battery. We see the old battery inside is exactly like this. This is another example. This is the sun. This is the PV module. The sun gives the energy to the PV module, and the PV module will transfer the energy to the voltage. This is another example. This is a coil. If connected to a power source, they will generate the magnetic field. If this magnetic field through another coil, this is a conductor coil, and they connect the bubble will be on. This is like the generator. We use the generator. Let's take the sample for a chemical battery and build a circuit step by step. Any source of voltage, including batteries, have 2 points for electrical contact. In this case, we have point 1 and point 2 in the left diagram. This is point 1, this is point 2. And the horizontal lines here, these horizontal lines of varying lengths indicate that there is a battery. You see they have the in horizontal line, longer, shorter, longer, shorter. And they first indicate the direction which this battery's voltage will try to push electrons through a circuit. The fact that the horizontal lines in the battery symbol appear separate and those enable to serve as a path for electrons to move is there is a chemical liquid inside between the 2 plates. You see this one? Between the plate, they have a liquid, chemical liquid, like the zinc sulfate and the copper sulfate inside the battery. So that means the electrons go through and pass through this battery inside and go back to here. In real life, those horizontal lines represent metallical plates immersed in a liquid or semi-solid material that not only conducts electrons, but also generates the voltage to push them along by interacting with the plates. Notice that the little positive and negative signs to immediate left of the battery symbol. The negative end of the battery is always the end with the shortest dash, and the positive end of the battery is always the end with the longest dash. We have the experience in our life. This is a mouse. Most people will know this is a mouse. Inside, you see here, they have the battery. They have the positive, negative, positive, negative. And you see, you put the battery inside like this, positive, negative. Since we have decided to call electrons negatively charged, the negative end of a battery is that end which tries to push electrons out of it. Likewise, the positive end is that end which tries to attract electrons. The same principle holds true for the water reservoir and the pump analogy. Without a return pipe back to the pump, stored energy in the reservoir cannot be released in the form of water flow. Once the reservoir is completely filled up, no flow can occur. No matter how much pressure the pump may generate, there needs to be a complete path circuit for water to flow from the pump to the reservoir and back to the pump in order for continuous flow to occur. This is a pump. If this reservoir is full, the pump cannot put any water go into the reservoir. Same with the electric battery. Is a battery, if it's only the battery, no connection between the 2 points, there is no flow between the 2 points. We can provide such a path for the battery by connecting a piece of wire from one end of the battery, from here to the another, from here to here, forming a circuit with a loop of wire. We will initiate a continuous flow of electrons in a clockwise direction, like this. So long as the battery continues to produce voltage and the continuity of the electrical path is not broken, electrons will continue to flow in the circuit. Following the metaphor of water moving through a pipe, this continuous, uniform flow of electrons through the circuit is called a current. So long as the voltage source keeps pushing in the same direction, the electron flow will continue to move in the same direction in the circuit. This single direction flow of electrons is called a direct current, or DC. In the later videos, electrical circuits are explored where the direction of current switches back and forth, alternating current, or AC. But for now, we will just concern ourselves with DC circuits. Because electrical current is composed of individual electrons flowing in unison through a conductor by moving along and pushing on the electrons ahead, just like marbles through a tube or water through a pipe. The amount of flow throughout a single circuit will be the same at any point. If we were to monitor a cross-section of the wire in a single circuit, counting the electrons flowing by, we would notice the exact same quantity per unit of time as in any other part of the circuit, regardless of conductor length or conductor diameter, like this. It is similar with the water pipe. If the water pipe diameter is bigger, then the water flow is slower. If the water pipe diameter is smaller, then water will flow fast. The total amount or total quantity per unit of time is the same. If we break the circuit's continuity at any point, the electric current will cease in the entire loop, and the full voltage produced by the battery will be manifested across the break between the wire's ends that used to be connected, like this. This is the circle. This 2 point, if break here, and this point is the same with this point. Whatever inside have the resistor or any others, because there's no current flow. So this point is exactly the same with this one. And this point exact the same with this point, but they have no flow. So this battery means is the potential is already connected to here. So they have the voltage drop. This voltage drop should be the same with this voltage drop between positive and negative. Notice the positive and negative or positive and minus signs join at the ends of the break in the circuit, and how they correspond to the positive and the negative signs next to the battery's terminals. These markers indicate the direction that the voltage attempts to push electrons flow. That potential direction commonly referred to as polarity. Remember that voltage is always relative between 2 points. Because of this fact, the polarity of a voltage drop is always relative between 2 points. Whether a point in a circuit gets labeled with the positive or negative depends on the other point to which it is referenced. Take a look at the following circuit, where each corner of the loop is marked with a number for reference. This is a circuit We connect this 1, 2, 3, 4 point. So the point 1, point 2 should be the same. This is negative, because point 3 is connected to point 4. So point 4 is positive. So this is positive, and this is the negative. It means this 2 point, this point, the voltage is higher than this point. And if we blocking between number 3 and number 4, because number 3 is connected to through this maybe resistance, is connected to the battery negative. So number 3 is the negative, and the number 4 here is connected to the battery positive. So number 4 is changed to positive. It means number 4 voltage is higher than number 3. You see, we found in this circuit, number 3 is positive, and in this circuit, number 3 is negative. What's the difference? It means number 3 in this circuit, the voltage is connected to the battery, so it's higher than this point, number 2. So that means number 3 is positive. Number 2 is negative. And in this circuit, because this is connected to the battery negative, this point, because here is broken, it's breaking. So this number 3 is connected to the battery negative, and number 4 is connected to the battery positive. So number 4 is positive, and the number 3, compare the number 4, the voltage is lower, so it means it's the negative. It is impossible for us to say that point 3 in this circuit will always be either positive or negative, because polarity, like voltage itself, is not specific to a single point, but is always relative between 2 points. That's all about this current and voltage video. Let's review the main point we already learned. Electrons can be motivated to flow through a conductor by the same force manifested in static electricity. Voltage is the measure of specific potential energy per unit charge between 2 locations. Voltage as an expression of potential energy is always relative between 2 locations or points. Sometimes it's called voltage drop. So if you were doing the electrical job in the future, you have a lot of time to calculate the voltage drop, to decide the cable size, some wire size. You normally, according to the standard, the cable voltage drop should be less than 5%, or with the normal, like the company, we use them 3%. So when the cable is running long way, you have to calculate the voltage drop between 2 points to decide the cable size is enough or is big enough. When a voltage source is connected to a circuit, the voltage will cause a uniform flow of electrons through that circuit, call it a current. In a single one-loop circuit, the amount of current at any point is the same as the amount of current at any other point. If a circuit containing a voltage source is broken, the full voltage of that source will appear across the points of the break. The positive-negative orientation of a voltage drop is called the polarity. It is also relative between 2 points. Thank you for watching. See you next time.